How do planes fly? They have wings, but they don't flap them like birds do. Strange, but our video would explain it to you. Take a look at this demonstration picture of an airfoil. The upper surface is more curved than the lower surface, and air is parted by the airfoil and directed downwards. We base our explanation on the Kuta-Joukowski theorem for lift on a rotating cylinder including a vortex in the circulating air. According to the Kuta condition, stagnation point near the trailing edge, which is on the upper surface of the airfoil initially, always moves exactly at the trailing edge. This hence the presence of circulation around the airfoil, which displaces the stagnation point. To maintain the conservation of forces, circulation of the equal and opposite strings sets and leaves from the trailing edge of the airfoil. In the figure, the diagram on the left describes airflow around the wing, and the middle diagram describes the circulation due to the vortex. The flow on the upper surface adds up, whether the flow on the lower surface subtracts, leading to higher pressure on the lower surface as compared to the upper surface. Therefore, applying Bernoulli's principle results in a net upward force. The remainder of the force going to the right is called drag. In our experiment, we installed beads at both surfaces of our 3D printed NACA 23012 airfoil. Seeing that the upper bead moves faster towards the end than the other proves the lift theory we just mentioned. Next, we tried to find the influence of the angle of attack, which is the angle between the leading edge and the wind direction, on the net force consisting of lift and drag. We designed 3 thin iron rod tracks with different friction coefficients for the airfoil to slide on. The first one is wrapped by tape with very rough surface. The second one is not treated, and the third one is wrapped by tape with a very smooth polished surface. The angles for these cases are 20 degrees, 17 degrees, and 7 degrees. When the airfoil hovers at steady state, the net force equals gravitational force subtracted by upwards friction. Since the gravity stays the same, this change in the net force caused by angle change is reflected by the need for corresponding change in friction. And since net force is directly proportional to the ratio between lift and drag, we compare our data to an LD ratio versus angle of attack graph, which we obtained from an NACA-related literature. The results match visibly. In the process, we noticed that at some point when we changed the angle, the airfoil dropped instantly. According to theory, the lift coefficient of a fixed-wing aircraft increases with increased angle of attack up to a maximum value, after which lift coefficient decreases. At exceeding angles, a stalling takes place. Stalling occurs when the lift decreases. Due to flow separation, the situation where the fluid flow no longer follows the contour of the wing surface, due to high pressure gradients that overcome the fluid's inertial forces. During the experiment, errors may occur due to the rough surface of the 3D printed airfoil and its change in geometry when exposed to hot winds from the hair dryer for too long. But nonetheless, the theoretical predictions hold true to a conceivable extent. In this video, we chose to experiment with a common airfoil type. However, some airfoils are uniquely designed for special purposes. You would be surprised.